Amazing. Thank you. What an introduction. Best one so far, Colin. Well rehearsed. I suppose it's been 5 months in rehearsals, isn't it? So thanks for the introduction. As Colin said today, I'm going to turn off my camera just because of any lagging, and I can see a little bit of lagging here. So just to make it easy for you all and more professional, as Colin says. So some of the things I'm going to take you through are understanding how we're decarbonising in track, looking at CO2 and track renewals, the S&C of S&C, I'll explain that later. First in class low carbon track renewals, low carbon sleepers, recycled ballast, and also some lateral resistance testing, looking at sort of resilience of our track. So to kick off, where does this all hinge from? So Network Rail has its net zero policy. By 2045, Scotland 2050, we're going to be net zero. How do we get there is the question. So various standards, statements, policies have been put in place. And one of our main standards is ENV 015, where it's stating we should be looking at our whole life carbon. So we should be planning, developing, designing and delivering projects that are low carbon. We also made a commitment to Department of Transport that we would be calculating our carbon, managing our carbon and looking at whole life carbon cycles throughout all of our projects. And it's not just projects this is also for the day-to-day purchasing of materials that we bring in, which are actually what we call scope 3 within our carbon footprint. And those are the sort of embodied carbons from the items which we purchase. So it could be sleepers, rail, ballast. It could be anything for building and construction projects, overhead line, catenary, all of those things as well. So it's quite a large chunk. 97% of our carbon footprint is actually within those scope 3 embodied carbon materials that we use and the delivery of those projects as well. What do we actually mean by kilograms of CO2e? So when we're calculating carbon, we look at the actual amount of kilograms of carbon dioxide equivalent that's in a unit. And we look at different units. A unit can be a sleeper. A unit can be 1 meter of rail. It can be a 1 meter section, cross section of track, or a kilometer of track. So we have to define what those units are, or it could be a ton of ballast. And it's actually the warming effect of the greenhouse gases. It's not just CO2, it's all the other greenhouse gases as well. So it's that effect that we have from those embodied materials, from those materials that have the embodied carbon within it. So we calculate it using an EN standard EN 17472. This is part of the construction works and how you assess in civil engineering works and how you calculate carbon within that life cycle. We also have a PAS 2080 module, which has got the same stages here. So you've got stage A0 to A5, which is what we call the sort of cradle to gate, the gate being the construction site where we install. Before that, we've got the studies we do, whether there's concepts, whether there's pre-construction, the product stage. It could be product approvals, it could be product testing, it could be all the other design work we do in the background, the transportation of all those products to site, and then it's the installation of those products. So A5 is the sort of installation phase. We then have the maintenance or operation phase, which is B, where we might do some maintenance, some repair. Can be tamping, it could be grinding, welding, restressing, changing the odd sleeper, a bit of refurbishment, anything that's that doesn't warrant a full replacement. So full replacement would be a deconstruction, so that's C, where we'd remove the track and then we'd install the track again. So generally with track renewals, C1 deconstruction and A5 happen at the same time. We take out the old track, put in the new. Some projects haven't got old track to take out. They've got a new greenfield site or possibly a brownfield site that they're putting new track in, so that decommissioning or deconstruction doesn't happen. So we do have a beyond life cycle stage, which is stage D, and that's where you look at the recircular or circular economy and repurposing, recycling of products. So if you've got certain products that we know can be ground back down and then feed feedstock into creating that material again for the future, then we look at that sort of that circularity aspect as well. So we are priding ourselves as being the first railway that have set science-based targets. So we're using science-based targets for our carbon rates and carbon targets. We've actually set a carbon target within sleepers, where for 2025, we're looking at producing sleepers that are 50 kilograms of CO2 or less. We know some aren't actually meeting that at the moment, but it's a target for us. So that once we can show and demonstrate we've reached 50, we can then see how we can start to ramp down and get somewhere to net zero. So, and we've only got 26 years to do that. So yeah, time is ticking. So I'm just going to take you through the life cycle, well, the installation of track renewals. Many of you may have seen this before. It's data cut from the RSSB tool. So this sets a baseline from 2021-22, and it looks at the breakdown of the rail, the concrete sleepers, the locomotives, ballast, fastenings, and so on. Also the vehicles, the tamper, the geotextiles, and pads and insulators as well. So it breaks down and shows you that 41% is actually the rail, so that's the most sort of carbon hungry, and then we've got the sleepers after that. So there are main two track construction materials that are sort of giving us those high rates that they're basically where we need to sort of concentrate our efforts. And that's what we've been doing for the last 2 years. We've been looking at rail. We're not there yet, but we do have some green rail in the country. We've been purchasing some electric arc furnace steel, and we'll basically be using that as one of our trial sites. We can do there are other ways of reducing carbon by making things last longer. So we can use either longer lasting steel, wear resisting steel, or we can look at how we monitor our wear as well, monitor more precisely. And improving serviceability and circularity of materials and cascading materials, something we used to be very good at. We've probably stopped over the last 20 years, but we're now looking at bringing that back in to make sure that people can re-service and reuse our material, especially sleepers and rail, and there's even a bit on ballast you'll see later as well. So concrete sleepers, 26%. So we have been using low carbon CEM2. There's some CEM3 mixes coming out. We had 100 kilograms of CO2 per sleeper back in 2022, and we've now got that down to 60. In fact, I think the latest figure is around 56. So we're almost getting that 50 kilogram per sleeper. And that's the concrete, which everyone knows has cement and is, again, one of our biggest offenders in carbon. We do look at other things that can actually reduce whole life carbon. So things like undersleeper pads, increases the life, therefore reduces ballast, degradation, and improves the overall track system whole life cost and whole life carbon. Some other little bits on the side, recycled rail pads and insulators. It's there. It needs more of a, I guess we need a sponsor. We need that project to be up and running. So it's being mentioned, but we need some sponsor and direction for that, because it's quite a small amount, but every bit helps. So locomotives, not really within our gift, but we do have within supply chain operations, we do have the loco hauls, and we do have the haulage contracts. So we can look at battery powered electric vehicles, biofuels, all those other things as well. That work did start around 2 years ago, so we know there is a lot of work to do there. It's now more a case of the expense versus the carbon saving, which a lot of this is about, especially when we're trying to reduce our costs to make our track renewals the most the minimum viable product, where other things then start to take effect because we can't deliver the low carbon solutions at the same time. So going on to switch and crossings, we talked about the S&C of S&C, so the sustainability and circularity of switches and crossings. What a mouthful that is, but we realise we've done a lot of work in Plainline, and we really need to start to transfer a lot of this over into S&C. So how can we reduce carbon within S&C? What lessons have we learned from the sleepers, the ballast and the steel? Why can't we design, install and maintain S&C that has improved reliability and service life? So sustainability isn't just about the materials, it's about making things last longer and making them reliable as well. And can we make better use of our serviceable S&C, so recycling, cascading S&C as well. Also looking at what technology and equipment is needed to monitor and maintain S&C to increase asset life in the future. I'm not going to go into that here, but it's something that certainly intelligent infrastructure and other monitoring devices we're starting to use more often, and starting to monitor the health of our S&C in a lot more detail. Again, it's all to increase life and to make sure that we know when to maintain and when to react, and not do the reacting rather than actually reacting to it. It's more about actually knowing when it's going to fail and being in time. So just some examples here of what we can do in S&C. So we have some figures here. We have concrete bearers. This is the breakdown of an S&C component. I think this is a D switch a DVS turnout that we took as an example. So we have the concrete bearers. We have the rail, which is blast oxygen furnace to green electric arc furnace. The castings, the point equipment. Some things we have question marks there because we're not too sure what they are and how can we reduce those. But things we do need to be aware of, because there is a lot of carbon in our point operating equipment and point machines. And ballast. So we do know quite a lot about ballast and how we can reduce that. So in 2023, we've got the figures for 23, and then we've looked at what we can do for 25 with greener concrete in our bearers, which has started to happen already. Greener steel, that'll take quite longer than probably 2025 to come through, but if that did happen, if contracts were in place and the need is there, it just shows a huge 64% reduction there on the steel side there. And ballast, going from sort of new ballast to recycled ballast, shows a 50%. So overall, we're saving that 29,000 kilograms for that turnout, and we may do around 50 to 100 of these a year, so that could be quite a big saving. Most of those savings are in the green steel, so I've broken that down there, and some savings down there in granite. So we're looking at, on average, around about a 50 to 55% reduction in S&C in the future for introducing greener materials. So on the circularity and recycling, we have our Whitemore Recycling Centre, which recently hasn't been up to its full potential, but I think awareness is growing, and certainly the serviceability of their materials that they do rail, S&C, sleepers and ballast. We also have serviceable sleepers in supply chain operations that we do sell at a discounted price, dependent on their grade and their condition, so they can be used in lower category track lines as well, and generally they're about half the price of new sleepers. And you can see there we had 93,000 tons of scrap metal in 2016-17. So a lot of these are old figures, and there is a graph that shows these dipping down over the sort of CP5, CP6. CP7, we're not actually doing as much renewals as we were in CP6, but it is a slower start as it currently stands, which is increasing towards the end of the year. And you can see this bottom line here, 1.6 million has been saved from ballast recycled at Whitemore, and that's certainly where we do hazardous waste ballast, and we recycle the hazardous waste and turn it into normal ballast. And recently we're tapping into the ballast that we would normally recycle and sell to other parties. We're actually using it now ourselves to feed back into our ballast stocks, which I'll go through later on in the session. So what Whitemore can do with recycling, and what can be achieved in S&C. So there was a reduction in carbon footprint because we were using a cost reduction in the purchase price because they're available to us. It's just a price for serviceability and inspection. Reduced depletion of natural resources. We're not mining iron ore or concrete or so all those other materials that we're using before. So it's saving the depletion of those resources. Better availability for emergencies, reduced lead times, and also being used as a strategic spare sort of inventory as well, and bespoke component inventory. I think recently we were after some £109 rail, and we all turned to Whitemore, and they had some rail for us. So it's a pity they didn't have any £98 rail, but they can only go so far. So part of our work bringing all this together is to demonstrate this through our low carbon track demonstrator. And the mission here is to complete a demonstrator project showcasing all of these low carbon initiatives. So it's going to include the embodied carbon and transportation of all the track components, materials, including construction, the site activities and transportation, and also the plant and site welfare and so on. So this is all current approved materials or items suitable for trialling that provide a reduction of CO2 to provide extended life and improve circularity. Other technology utilised in the installation of track and site management is also being explored. So we're doing some of this work with Colas, and they're looking at greener site welfare cabins and greener tooling, greener small plant. So they're looking at the plant side and what goes on site for mobilisation. And we within supply chain operations and teamed up with route services are looking at sourcing the lowest carbon concrete sleepers, recycled ballast, and eventually, when it does become onto the railway, green steel rail as well. So this gives you an idea. Similar to what we did for S&C, we can reduce 64% by using SEN 60 green steel in place of oxygen arc furnace. 72 concrete sleepers, there's a 40 to 50% reduction there. Recycled ballast, 25 to 50% reduction, depending on the mix rate, how we blend with new ballast, because recycled ballast is not just completely recycled. We do blend it with new ballast as well at varying different ratios. Recycled pads and clips, that's something as another initiative that can be added, but within that section alone, we can save 40 to 50% within the clip section. And this total provides, when you look at how these are all summed up and accumulated, like we said, 40 to 55%. Some other items like undersleeper pads, although they very slightly increase the carbon of the sleeper by around sort of 3 kilograms or something very small. It's the whole life saving, the whole life carbon reduction that we can see then. So it's the whole life carbon modelling that we can do to look at reduction that we have there. So putting that into perspective, looking at supply chain operations and what sleepers we purchase. So in 2022-23 and up to 24, we were purchasing around 500,000 sleepers. So if you look at how that's divided, there is the table on the underside there, which shows a hardwood sleeper, steel sleeper, concrete sleeper, and the introduction of composite sleeper in place of hardwood and softwood. So it shows our sort of total volume of 503,000 there on that bottom right-hand corner, and the total CO2 for that. So looking at the same volumes, although we know for the start of CP7, it's going to be less than that because this was a CP6 figure, it will be less. But if we were just to say the volumes were the same, how can we show or demonstrate our reduction? So steel from British Steel, they're looking at reducing their 80 kilograms per sleeper down to 65. Concrete was 105 in 2022, and we're bringing that down to 52 in 2025. So that's a huge saving there. Composite sleepers, a small saving, but that's just on renewable energy and so on. But that's the lowest carbon sleeper that we have. And hardwood, as you can see, is very high, but that will be phased out. As you'll see later, that's a zero volume there due to its phasing out for composite sleepers. So volumes are based on previous purchased and CP7 planned figures. The 2025 used in this case is to show the sort of phasing out of hardwood for composite as well. So you can see where the hardwood goes down and composite starts to creep up there. And in sleepers, we're looking at a total reduction of 47% alone. So once you start to feed that back into the ballast and the steel for all track renewals, then you'll start to see the overall picture there. One of our suppliers, Cemex, I think Colin mentioned you guys may be visiting their factory. Thoroughly recommend that. We did a Reading Thames Valley PWI session there where we visited the factory, and Paul Craven is a great host, and he'll go through some slides and show you his route to reduced carbon or a greener sleeper, which is one of these slides which I took from Paul. So you can see where they were with Washwood Heath, and then when we started at Rochester, with the G44 concrete sleepers, and we're getting down to 47. And the 42, we're not there yet. In fact, we're somewhere around sort of 55 to 47, and we're getting to 42. So it does change by the month, and we're having to track it that accurately because of the mix changes and the steel we're using, recycled aggregates we're using, and other things that we're using in there to improve that and reduce the carbon. So I mentioned the ceasing of tropical hardwood purchasing. So in May 23, we approached the executive leadership team board, which Andrew Haynes sits on, and the head of sustainability. And we discussed the plan to phase out the purchasing of tropical hardwood plain line sleepers from Brazil. And this was in place of a composite sleeper substitute. So the reasoning behind the paper showed the business change, the benefits, the use case, the cost impact, the green impact of that change, and how that can be introduced. The board accepted it, and we've now since so we have 2 weeks to go before we stop that procurement of sleepers, of hardwood sleepers. The installation ban will start June 24 as well. There is sleepers that have been, I guess, stockpiled and being used, hardwood sleepers being used, so that will be difficult to sort of, you know, to mandate, but we haven't changed anything in a standard. It's more a procurement strategy that's forcing this at the moment. High speed approval is expected, I think June, but later now. I think we're looking at approving a high speed composite sleeper for up to 125 miles an hour. But the important message we've sent to a lot of people is that switching crossings hardwood bearers are still being purchased. They're still available for adjustment switches and gathering panels and all the other sort of plain line panels that we use them for as well. So within S&C. So why did we choose plastic sleepers in place of composite, in place of hardwood? The main reason for us was the circular economy, the reuse of plastic, recycling plastic back into a sleeper that's locked in for a life cycle longer than 50 years, where in a bottle it's measured in months, and in a sleeper it's measured in decades. And we know with hardwood, at the end of our hardwood life, the cascading of those sleepers really isn't possible, because they're rotten, and the grading of them is quite difficult to grade accurately. So that's why we've gone to the composite. And the recycled plastic SciCut, which is the alternative to hardwood, does tick a lot of the boxes in terms of the performance in comparison to hardwood. So the longevity, you can drill into it, you can fix into it, you can cut it, you can do all the things you do with timber. So it's very similar to timber. So statement there, really, hardwood is not reusable or recyclable, nor can it form part of a sustainable circular economy. So that's, you know, that's where we decided to go to plastic. Just a bit of guidance on use, because a lot of people are saying, where are we best to use these? So they are used in place of timber, hard and softwood. We also banned softwood sleepers in 2022. They have the same depths, 132 millimeter and 152 millimeter deep, same width, and they can come at the same lengths as well, and can be short-ended, and also chamfered. We can cut the bottom corners off if we have sort of tight tunnels to work in as well. So they are more resilient. They're less likely to split when you cut the corners or you cut the ends, because with timber, when you do that, you're very close to a chair screw, and the chair screw hole will sort of stress the timber, and the timber then will, over time, will split, and you'll get a broken timber, and then you'll lose the fixity of your base plate. So, and you don't get that with plastic sleepers. All base plates work. We don't allow rail spikes or the BRS1 plates, which is the old spiked chair and rail plates. They're not permitted to be used. They do weigh similar to timber. Density is 840 kilograms per cubic meter. And they're ideal for weight, depth and length restricted sites. So where we've got viaducts or structures, or we just can't fit a normal sleeper. And also where, if you were to use a concrete sleeper in a shallow ballast area, where you don't have the ballast depth, then plastic does lend itself because it's more resilient, it's softer, it dampens, so you don't get those sort of hard stresses and loads sort of creating the concrete from breaking and cracking. So overall, looking at our 2022 baseline and this going into this year with the first-in-class trials, we're showing a 53.54% decrease in carbon. And that's going from the steel, from the sleepers previously purchased in 2022 to what we have now, the lower carbon alternatives, electric arc, rail, and recycled ballast. So by including those, and this will become a business as usual. We were in danger of introducing it and actually no one realizing we've introduced it and then saying, well, we just halved carbon overnight, but no one really saw it. So we better tell people we're doing this, because otherwise they'll say, what are you doing about reducing carbon? So this is why we're here. So I mentioned about the smalls, what we call the jewelry of a sleeper. So that's the shoulders, the clips, the insulators, the nylons, which more often than not get thrown into the ballast or wasted, or we just don't recycle them. So we're looking at rail pad recycling. We do for a form of rail pad recycling at the moment, not back into rail pads, into equestrian matting and other sort of reuse rubbers. But we've got to make sure it's the right type of rubber, because there's so many different types of pads out there. So we need to make sure that they are all compatible as well. Insulators, so mainly nylons that we're looking at there, how we can reuse those. There isn't a real good feedstock. Our biggest logistical issue is making sure there's a feedstock of these, making sure at source, when they're removed, they are collected, they're put into a skip, the skip's collected, the skip goes to the supplier who's making it, and they've got a good feedstock, because all of these rely on feedstock. If we can't get a feedstock more than, say, 15-20%, then it can become a bit cumbersome to do this. So we've got to look at that tipping point of where freight, haulage, and all those other things come into it, and also the effort to sort through and pull these into different bags as well, like we do with recycling. We do a lot of that with our own initiative at home, with our own recycling bags, but we need to start doing that at our material handling depots as well. So I think having those campaigns and strategies in place will help this in the future. This is all early doors at the moment, and we know that some suppliers are actually having a recycled content within their rubber products. So they're already doing that. We're already having sort of 10-15% recycled products within there. It's how much can we push that? Can we go to 25%? Can we go to 30%? And does the performance of the pad or the nylon or any other plastic item in there affect the performance of the track? Of how we fasten down our rails and so on. So that's one thing we're looking at with the suppliers as well. Steel recycling for rail clips, there's a lot of steel there, so there's a potential saving of 800 tons of CO2 a year there if we got all our clips that we purchase every year on a sleeper, because of the 500,000 sleepers that we purchase have all got clips on them, so there's a massive saving there as well. And do we prematurely throw away steel clips? There's no way of really testing the serviceability of clips. You can't look for an age for it. They just look rusty, and you think, nope, they're no longer usable. So is there something we can do in that sense? So our next and latest news item really is recycled ballast. This started I think it started around 8 years ago, when one of the members of the QA team started to look into recycling ballast and reusing ballast, and we have been doing it for 50 years for ballast cleaning. The high output ballast cleaner uses ballast. It does it on site. It sieves, washes, processes, and pours it back underneath the sleeper as it's cleaning the ballast under the track through the machine. So we have been doing it. Do we understand the performance of that? Is there any issues with doing it on a separate system for processing ballast that's not part of a high output ballast cleaner train? And can we basically produce ballast that's just as good as new ballast. So that was really the target for us, and that was the aim for us. So, and what the aim here is that all future supplied ballast will actually include an element of recycled blended ballast. It could be 25% recycled, it could be 50%. When the feedstocks come up higher, it may even be 75, but it's not likely to be. So I'd say in 2 or 3 years' time, we're probably looking at a 50-50 new ballast mixed in with recycled ballast. Getting to a stage where it's 100% recycled, that's going to be 20, 30, 40, 50 years down the line. But it can be made available if we just don't mix new ballast into it. But we at SCO really just want one price for ballast, and it's a blended ballast mix that you get, rather than having a separate material order for new ballast and a separate material order for recycled ballast. So it's a blended product that has no difference between the two. Benefits. Most of these benefits are depletion of natural resources. There is a 50% reduction because we're not quarrying, we're not blasting, we're not machining, we're not processing. All of the items that you do when you're basically quarrying for ballast. Also, with quarrying comes biodiversity issues. You've got the local habitat, you've got the plants, you've got the animals around the area, the ecology system that's affected by a quarry. Yes, quarries do take over the landscape, but they shouldn't really be there. So, it's trying to bring that nature back into it. I know some quarries have had a really good job of basically reinventing themselves, being used for other things, and for other purposes, which is great. Certainly for sort of leisure activities and things. So those sort of things do happen. What we've also found with the recycled ballast is the washed ballast does reduce the ballast dust particles, which is a health issue. So we do get fine dust particles that once in the air does become a health issue. By the washing process and mixing process and washing again, we do reduce those ballast dust particles. So that's another bonus from this. We do get some sand out of this as well. There's sand that does come out, the fines that come out that we can use for sand blankets. And some smaller aggregates we're actually using and trialing within sleeper manufacturing as well to see if we can use those for sleepers. And also pathway infill is another sort of use of some of the sort of finer material that comes out of that. So we looked at the risks and disbenefits that introducing recycled ballast can present to the railway. The variability of quality of supply, the consistency or inconsistency of granular material, impurities from excavation, loss of angularity, loss of particle roughness, change of particle shape, degradation rate, ballast migration, reduced strength, that's vertically and laterally, and also reduced lateral stability of the track itself, and the organic content variability. So looking at the branches and twigs and other organic content that we get in there as well. Sorry, I just need to let my dog in. He's trying to come into my room. Okay, so this is some testing that we did with compaction testing with baseline fresh ballast and synthetic ballast and recycled ballast. So we're basically looking at the compaction rates here and also looking at how, when we push a sleeper through the ballast, how its lateral resistance is measured and compared. So we're looking here at the black line is fresh ballast, and the red line is recycled ballast. So the red line is showing that we've actually got a high level of lateral resistance for the sleeper as we push it through the 10, 15, 20, 25 mil, 30 mil, up to 40 mil displacement. So this is also to look at the difference between dense ballast and also loose ballast. So it's consolidated and loose to see if there's any difference in performance there as well between the ballast types. We did some tests on ballast, the particle size distribution of the ballast as well, to see how it fits within our Network Rail Standard 8100, and how it shifts more to the sort of lower size. We're getting smaller rocks and smaller particles that are coming through the system. What we generally found was, if you look at the ratios of mix, so there's a 75% recycled mix, a 50% recycled mix there, which starts to come back into the PSD range, and that's where we noticed that mixing of new and recycled is probably our best, particle size distribution consistency that we're going to get as well, mixing with new. So 25 to 75 recycled is where we're looking at that. So generally the smaller particles do mean that we are getting a different consolidation layer as well. We also looked at the porosity. It did reduce by 2% because we're getting higher density, so the ballast is compacting more, so we're getting less voids, if you like. So as porosity decreases, density will increase. But we did notice that the reaction or the particle presence of the fine materials aren't there, and they won't be there right at the start as they would be with new ballast. So you won't get early ballast clogging from the dust particles. And as the ballast starts to bed in and work harden, you get the fragments that break off. Those fragments then fill those voids. Now, because recycled rock or recycled ballast has already been work hardened, it's already had the corners knocked off and has already had that sort of hardened process, you won't get that as you will at the same rate as you will with new ballast. Once you do 2 or 3 ballast tamping cycles, you start to get the breakdown of ballast, and that's when fines start to create as well. So this will help reduce that that sort of clogging of ballast. Now my dog's starting to play with squeaky. I do apologise about that. Seems to be very excited to see me. So the approval status, we actually had this the recycled ballast approved in May, just gone last week. So the lateral resistance testing, the University of Southampton testing all showed, and triaxial testing all showed we had a good test. The abrasion testing for blended also showed that we had good values. So that's the Micro Davao and Los Angeles. So the approval was given. So full acceptance was given for supply of recycled ballast blend to a maximum of 75% recycled spent. So we've capped it at 75 for now, rather than the full 100% recycled, because we realise that the mixing of 25% new does give some advantages as well. The main part of this is adopting a QA process, because we need to have an ongoing QA process that checks the consistency for the recycled blend and ballast also. So that's the main part of that. Two other things we've been working on are within our sort of sleeper strategy deliverables. One of them is the new sleeper technology specification. So this is looking at a new standard for sleepers that looks at low carbon, circularity, higher performance. Basically, any novel sleeper out there that could be a hybrid of concrete, it could be a different mix of composite, it could be various different things. So it's putting some performance requirements and business requirements together for how we would use the sleeper, how we'd install the sleeper, how we'd maintain a sleeper, and for whole life benefit and whole life carbon and cost benefits as well. But at the same time, trying to make sure we keep a low unit rate cost as well. So that's a standard that's actually going to be published in June 24. And that's one of our first standards that's sort of introducing a low carbon target as well, of 50 kilograms per sleeper. We've also got some sleeper guidance document coming out. That's an SCO document that I'm drafting for guidance on sleepers. So the people that purchase, design, specify, order, use, and maintain, really where they may need to replace sort of sleepers as well. Some guidance there. Certainly, as we've now sort of increased our sleeper types, we've got composite sleepers. It's also steel sleeper. Some guidance on steel sleepers in there, and under sleeper pads, lerps, and all those other things as well. Just an update on where we are with approvals for all of these new products. All of the concrete sleepers were approved in 23, so May, June last year. So these are the low concrete mixes. The Cycot composite sleepers have been approved for the last, since February 23, they're updated. So we've now got them up to 100 miles an hour, Cat 1 to 6 on the Cycot 155 sleeper. We're also doing some trials at 110 miles an hour, and we're about to approve the adjustment switches. So composite sleepers using adjustment switches as well. Secretary 160, so this is the FFU composite sleeper, is also on trial for high-speed usage. So we're trying that up to 125 miles an hour. Recycled ballast, now approved. Recycled pads, we do need a sponsor, so that's what we're looking for as a sponsor for that. And then there's the Sarsdale 1060 green steel rail, so approved, but we do need to run some, we're doing some weldability testing on that as well, and looking at retendering in 24 as well, and how that might be part of the new tender. So I was asked previously just to provide a bit of guidance to designers on low carbon track designs, what certain tweaks or reducing ballast depth can do in terms of carbon. So we did some calculations, and so if you were to look at reducing the excavation depth from 300 millimeters to 250 millimeters, you can save around 6% of the total track CO2. That's mainly on the ballast material, the plant, and the train use. So it's not a big figure, but it does 6% can stack up. Installing LERPs do actually add, so LERPs are lateral and resistant plates, does actually add an additional 4% to our track renewal CO2 unit rate. So it's quite high. When you think a LERP is almost as similar to the CO2 that you have in a concrete sleeper, so that's quite a high figure. Using recycled composite in place of timber sleepers can save up to 18%. Using recycled ballast can save up to 2.5%. Depends on how much feedstock and how much recycled versus new we used. So track standard TRK 2102 design and construction of track does specify these requirements for how we design track. So, the actual design and construction standards do state the minimum dimensions for these as well. But the material choice does default to lower carbon track material in the future. So, we still do need to choose what material type we are using. And lastly, using undersleeper pads can extend ballast and track life by 20, in fact 25%. I think other studies have showed. We've picked a very pessimistic figure there, just so that we can align that to whole life carbon savings, and cost savings can be made. So previously some of that was done on cost saving, whole life cost, but now we can apply that to whole life carbon savings as well. Working sort of the serviceable sleepers area, and the TA, along with I think it's Scotland and possibly Southern, have been working on how they can or service the sleepers themselves, because previously it was only route services colleagues or engineers that could do this. So they're trying to adapt this internally within their own teams. So local cascading rules can be adopted to retain sleepers within the route. So they're basically cascading in the route. They don't have to go off to Whitemore and then get used elsewhere. So they are actually using their own sleepers. So, they're managing their own process and cascading their own materials like we used to do a long time ago. It's really just readopting that philosophy. Assessing the soffit can only be carried out once the sleeper's removed. I mean, you could do samples and pull out 4 or 5 and assess those, but really you can't tell until you've removed the sleeper. So you can't tell from the top really until you've actually looked to the underside of the sleeper. And there are some red clauses within TRK 4001 that are being challenged at the moment to see if we can make those an amber clause, which gives a little bit of flexibility to the route then to be able to do various other things and make other decisions. But I think ensuring engineers are competent to carry out the assessment is a key one. Making sure, because it is quite a subjective assessment, so it's making sure it's clear and accurate and how you actually assess them. And at the moment, Whitemore stock is the sort of main point of supply for serviceable sleepers as well. So that sort of still retains. As part of our sleeper guidance document, we've also introduced this LCA table. So this has got the new 24-25 prices on here. It's got our unit rates, and it has the so you can see where serviceable sleepers do reduce the unit rate quite considerably. It has the whole life cost, the average life expectancy. And what you can actually do with this table is you can look at for each case by case basis, you can look at the average tonnage or that you're installing this on. So if it's 40, 25, 30, 15, these figures can be changed and amended, and then you can see which sleeper works best for you in whole life cost terms, whole life carbon terms. The performance on the right hand side of the sleepers, obviously that stays the same, but lateral resistance performance is down there, so it's showing you which ones have got a high lateral performance. Really the only high lateral performance sleepers we've got are sleepers with under sleeper pads. The other ones are sort of medium to low, quite a lot of lows there. So, you know, in terms of trying to improve trap resistance and buckling resistance, we should really be thinking about using the sort of the higher lateral resistant performance. And degradation of ballast, so that sort of ballast life and so on, that's also been scored in there. And also stiffness strength and so on. And to the right is the carbon figures, so the carbon per sleeper, and then the whole life carbon sort of based on its expected life as well. Lots of caveats and sort of notes down there to explain how things were derived and where these come from and so on, and some guidance on the use of this table so that people don't use it incorrectly. You know, use with caution. If you want some advice on it, come see us. We can tell you how to use it, and we can do some assessments for your projects as well. So a lot of this work that you'll see on that table for the lateral resistance testing came from the University of Southampton lateral resistance testing we did with all the different sleeper types. We also did some different ballast profile types and ballast types, so recycled and consolidated, non-consolidated as well. So it is as basic as pushing a sleeper with a you can see the girder there, that's sort of to transfer the load from this ram arm onto the sleeper and pushes it through the ballast. So we're looking at the load to displace that sleeper by a certain amount. Here we have a graph showing the test results when we compare a sleeper with a lateral end resistant plate. So you can see the black line at the top is a G44 with a type 1 USP, which is just our normal USP that we use, a 3007. And below that you can see yellow, which is this G44 with a lerp. And we repeated it because we weren't too sure about the results. So we repeated it again, and we did it, I think, 2 or 3 times the test to try to get this. And it was showing that at those early stages that actually a USP is higher in lateral performance than a lerp. What a lerp can do, though, is it is permanently stuck in the ground. So if there is any voiding, obviously, then you know a lerp will be there. But what you got to remember is a USP stops voiding because it provides you know, a more contact surface area, and it stops those high areas where you get ballast degradation, ballast migrating and ballast moving, and smaller fines coming in as well. So voiding is more likely to happen with sleepers without USPs. So it does demonstrate that USPs perform just as good as. We've been considering these in our track standard TRK 2102. We haven't made a final decision yet. We think more scientific evidence is needed. So more testing and more guidance from other countries as well that have done this. So we're just pausing on that at the moment, but we are looking at how we can reduce the amount of lerps we use, because they are quite expensive and they are quite a pain to install as well. So this is the overall table showing all the different sleeper types. You can see at the top, and we've got the weight there as well, so it gives you an idea about the weight. At the top, I think those weights do look slightly different. I think it includes the beam on there as well. It's got some weird, yeah, so the weights aren't accurate. This was taken from Southampton. They included the weight of the beam as well. And you can see there, so this is all of our different sleeper types. So steel is quite a good lateral resistance. So that's at the bottom there. It's a horizontal load of 8. G44 with lerps being around the highest, and same with G44s with USP being the actual highest as well. So yeah, this is just a way of giving you an overview of how all these different sleepers perform naturally, and if you're choosing what sleeper you'd like to give you the best lateral resistance for the future and resilience certainly in what we know to be increasing rail temperatures and increasing buckling risks of our railway in the next 5 years, then it's making sure we choose the right sleepers for that task. And this is just for ballast, different types. So it's this is dense ballast. So this is the synthetic. We created a worn synthetic ballast. So it's basically 25 to 30 years old. So it has a certain amount of fines in there. We've got the recycled ballast, and we've got some fresh, brand new ballast. So we were looking at how sleepers perform in those sort of different stages of ballast life as well, and different types of ballast. So we can see if there's any concerns there. Certainly with introducing recycled ballast, and as ballast becomes more clogged and there's more fines in the ballast, does that affect the lateral resistance over time? And as you can see through here, um, it does depend on what type of fines you do get. In some cases, you find the sleeper actually almost cementing itself to it because it's become sort of cementitious, and you won't see any lateral resistance moving. In some cases, you just see so many loose fines in there that it's not doing its job as it used to, and it's so you get lots of basically you get settlement vertically and laterally as well, because you haven't got the ballast particles locking against each other. So I think that's it, all summed up. That's our current Network Rail of sustainability targets are what we're doing, what we're I guess improving and introducing to everyone. And I don't know, Colin, if you wanted to go through and do any questions. I'll stop sharing.
Yeah, absolutely. I mean, first off, obviously, thanks, Darren. There's some big numbers there, and there's been a significant results achieved thus far. You're talking about, recycled sleepers at 50% of the cost, which is great. 53% reduction of track materials in carbon. And that design guidance document you got there, that looks, all based scientific evidence, etc. That looks really, really good. So, and who would have thought S&C on a PWI conference would stand for sustainability and circularity? We're all thinking switching crosses, but good. No, so there is some questions in the chat. We've
Brilliant.
got now some of this you might have covered, I don't know, but it says here, Ramona, what about the latest research on not using LERPs where we have USPs and geometry seems to be appropriate?
Yeah. Okay, so we've presented the evidence from Southampton to the working group for 2102, which basically specifies where lateral end resistance plates should be used. It's currently on hold. We're looking for further evidence to back this up. Everyone gets the science. They understand that undersleeper pads increase surface contact, which will give you a good friction between the sleepers and the ballast. Rather than just ballast skidding on top of a concrete sleeper. So we do get that. We also understand that LERPs will probably being over installed, and we're probably over specifying them, but we don't know. We've got to go back to the first principles of why we started using LERPs in the first instance. We've got to understand our track buckling calculations. We've got to understand why we started adding these things in the first place, and why we started saying add 5 degrees for this, take 5 degrees off of that, where you've got LERPs on certain radiuses. And there's some work also done for Intertrack 3 on lateral dynamic modelling, and that needs to be finalised as well, because we don't think we've got anything out of that can actually give us evidence to say, actually, this is where our risk lies. This is how we manage it. These are the certain areas we need to go into. So we haven't got we've got some of the answers, but we haven't got all of it yet, and more evidence is needed. We need to speak to the other railways that have actually changed their standards already and aren't using LERPs in place of USPs, and understand that I'll understand the risk better as well before we change.
Can I just make a comment, guys?
Yeah, sure.
Thinking back to days as a maintenance engineer, when we did have buckles in plain line in these sort of circumstances, it was usually where there were voids under the sleepers. It might be a dip well or a dip joint or something like that, but basically you couldn't take into account too much the contact surface resistance between the underside of the sleeper and the ballast. So if the comparison between maybe a G44 with a USB and a twin block sleeper which relies a lot on the resistance on the two faces at the ends of the sleeper. It wouldn't be a direct comparison in a voided situation, if you understand what I mean.
Yeah.
Yeah. So before you start taking LRPs out, because the G44 in theory has better resistance, and that relies upon the underside of the sleeper, just bear in mind the voids, because that's where I've had track buckles before.
Yeah.
Wouldn't want to see it happen again.
Absolutely.
Yeah.
I think it's changing construction stiffness. It's where you're going from a sleeper type to another sleeper type, because that's where voids can create, or discontinuities in rail. They're absolutely, yeah. But what we're also saying is, if you had some undersleeper pads in there in the first place, you wouldn't get as much voiding because it spreads the load, and certainly at joints and welds. So there is that. You wouldn't get the voiding if you had more undersleeper pads in the first instance. But you're right. If where you can't put undersleeper pads, or you've got track that is voiding, then yeah, undersleeper pads aren't going to help you.
Yeah. Okay. We could talk about it all night, but basically, the voiding usually happens where you get an impact on the rail. And regardless of what you got on the underside of the sleeper. Anyway, yeah. Okay. All right. Thanks. I've got a couple of questions. Yeah, go on. Sorry.
Shall I just go on to the next questions?
Yeah, I think they're mine anyway. Yeah.
Can you see him, Darren?
Yeah.
Yeah, I've got them. Yeah.
All right. So the first one, does the reduction in CO2 with concrete sleepers, presumably due to the using SEM2, does that take anything away from the service life of the sleeper, do you think? Or
no. So it's the testing we do within the EN testing and our concrete sleeper testing. We still have to do. We do all the performance testing, abrasion testing. We have to do table wear abrasion. We do all sorts of tests that show the sleeper life, fatigue, bend test. None of that's changed. So all of that performance requirements that are in those standards has not changed. We've had to make sure we maintain those. So yeah, there is no performance downside from using those new mixes, which is the main thing. Yeah,
that's good. And the other one is composite sleepers. I appreciate that they're just being approved for higher speeds, but do you see the use of those replacing the use of concrete sleepers in time, and even on track renewals?
So main use at the moment is where we'd probably use timber as a guardrail, light installations when we got issues. But as a direct replacement for a G44, I'd say no. I think the cost drivers they outweigh all the other. And what we have done in the last 2 or 3 years is we have reduced the amount of CO2 in concrete to sort of bring it into modern equivalents, if you like. And they're also looking at crushing end of life, crushing them and making them at least 90% recyclable with the material. So it goes back in to loop back in, so we can take out the steel, the aggregate, the shoulders, all the things that made up the sleeper, and push that back into the loop as well. So there's work being done on that. And I think the serviceability of sleepers, using them on the lower track categories, we need to get better at, and that will improve it. So I think concrete is still here for a while.
Okay. That's great. Yeah, thanks, Darren.
Good. I can't see any other questions, and I think it's probably partly because your presentation was so slick. So I think you probably answered any questions that the guys had. So all that leaves us. Phil, would you like to do the vote of thanks?
Yeah, sure. Well, just say thanks for coming along and spending the time putting the slides together for us today and spending time with us today. It's an excellent presentation, a lot of detail covered in all aspects of PWA relating to the sustainability and decarbonisation subject. I know people have been wrestling with this for years, and you particularly have, and you've got right into the detail, doing all the calculations and getting the universities involved in this. And it's quite obvious from the presentation today how much work has been done on this, and some really good stuff coming out of it. So I think it's fantastic, personally. great for the environment. Yeah, it's yeah, really heading in the right direction as far as I can see. So so yeah, from Ashford Section, really big thanks, Darren. Yeah, love to have you back in a couple of years to talk about this again. So yeah, it's getting on. But
yeah, no,
yeah,
love to. No,
yeah,
thanks for inviting
yeah.
me, Phil and
Thanks
Colin,
very much. Yeah,
and yep, we'll be back again soon for another one.
Good
yeah.
stuff. Okay, well, thanks, Darren. Thanks.